Hello, today we'll discuss about the single-site two-way ranging. So single-site two-way ranging is one of the mechanisms used in the UWB to identify the precise distance. So basically how it works, so there's a complete documentation is given in the UWB user manual. I'll be posting in the description and my Git repository. So where you can see, so I'll just give you overview of the single-site two-way ranging, how it's working. So in single site two-way ranging, there are two devices are there, device A and device B. Device A will be acting like an anchor or initiator. Device B is acts like a tag or responder. So device A is sends the data with some timestamp, with some uh, timestamp, and it records the timestamp when it is transmitted the data. The moment it transmits the data, the internal clock in the device A will be start counting the time. And the moment device B or receiver, responder or the tag receives the data from the anchor A or device A, it records the receiver to the timestamp. Then it also starts counting the data time and it processes the data and sends the back. The moment device A receives the final data, so this completes the one transaction. It also records the received timestamp. Now difference between the transmitted timestamp and the received timestamp will be given as a total round time, and the difference between the received timestamp from the receiver device B and transmitted timestamp will give the T replay time. The difference between the T round and T replay divided by 2 will be given the time of the flight of this complete transaction, and this time of flight is multiplied by the speed of light will give the exact distance between the device A and device B. So that's how the single site two-way ranging will be calculated. And there are little bit offset will be there, we'll call the clock offset, that can be negligible as per the register settings in the UWB device. So I'll just walk through the code. There are two codes are there, I'll be sharing with you. The first code is a transmitter or the initiator, or we can call a device here. The the second code, the right side code, is the responder on device B. Okay. So in the beginning of the program, it will call the dw3000.h library files, header files where all the function prototypes are defined. Then this is the name of the program. You can change it as your wish. The next three lines are the SPI connections from the ESP board to the UWB chip. Don't change it until unless you are using the other board like Corvo. The next comes about the configuration of the UWB. So this is very important. There's a lot of materials available in the DWB user manual and datasheet. That UWB works in the two different channels, channel 5 and channel 9. Right now we are using the channel 5. What is the preamble length? We are using 128. Pack code, preamble acquisition chunk, transmission code, transmission preamble, receive preamble, and a lot of information is available. And here we are using the STS mode of the STS is called scramble timestamp. It's more secure way of communicating the data. So in the initially for this simple distance measurement we don't need it, so we made it off. And PDO is also off. The PDO means phase difference of arrival, which we are not doing because we are using flight of time of flight. The same thing will be described in the receiver part also. Coming down, receive delay in millisecond range delay. So this is a minimum delay between the two messages. The next one is called the transmission antenna delay and receive antenna delay. Transmission antenna delay is so this can be configured to get a more accurate results. There can be tunable as per the data sheet. The next comes the transmission poll message and receive response message. The transmission poll message where the data is be transmitted by the transmitter, and upon that and receive RX response message is what the data is received. The common length is at 10 bytes. The index starts on the array index number 2, and response message poll RXT transmission index and response message responded transmission timestamp. So from the 10th bit onwards, you will be having the 4 bytes will be calculated for the responded message poll receive timestamp, and from the 14th byte onwards it will be calculated as responded message response timestamp, and each are 4 bytes, so it's denoted by the 4. The same thing will be defined here in the receive side also. Scrolling down, this is the receive buffer length. The code is very much self-explanatory, and you will be in poll TX to receive RX delay. So this is a delay where the transmitter will be waiting from the transmission of the first message to receive of this replay message. And receive respond or RX timeout is defined that how long the transmitter or initiator has to wait before it's declare a transaction as invalid and start a new transaction. So basically in the setup we'll be doing some configurations related like UART installation where we'll be sending the debug prints. Next is printing the app name, Hadoop code, then it configure the SPI, then it waits for the 2 seconds to get established, then it will check whether the UWB is ideal or not, then it check whether UWB has any installation error is not. If everything looks good, it will enable the few LEDs glowing on the UWB chip. Then it will configure whatever the messages or the channel we configured in the beginning of the program. Then it will set the antenna transmission and receive antenna delays. Same thing we'll be doing on the receive side also. Then it will set the poll TX to receive RX delay, that is a 400 240 microseconds. So here UUS means UWB microseconds, which is way lesser than UWB microseconds. The next is the receive timeout. It's 400 UUS. UWB microsecond is very smaller value than the normal microseconds. Then we set the enable the LED pins. Yeah. So here the some additional code I added to get a moving average, to get a smooth value of the data what we are getting. Yeah. So coming to the while loop. So here the main loop is starting. So here you can correlate this complete transaction with this array. So as soon as the code enters into the loop, first it transmits the data with this. So this you can correlate device A is sending the data. Once the device A sends the data, it will look for the status register. The status register is available, the 2-bit register available in the user manual, where each bit denotes the significance of the register, like a transmission error flag, receive error flag, or any errors are present. So once it waits for the proper transmission is happened, then it will go and increment the frame sequence. This only to tell that every time it's sending a new sequence, it's not a mandatory field. The next, after sending incrementing the frame for the next sequence, code enters and waits for the receive bit is set or not. Once the data is received in the UWB, the receive bit is set, so then it will enter into the safe condition. So the moment the controller device transmit the data, you can see in the responder device B, it's always enabled to receive a new data. Once the transmission is transmitted from the device A, the the logic or the flow goes to the receiver side, where the receiver is already ready to receive the data. Once receiver is ready, receives the data, and data has been received, so it will go here. Then it will check that the data is perfect, good or not, as per we defined in the beginning, so that no other corruption, or it will ignore any corrupted data, or it will ignore the data sent by some other device. Once the data is verified, then it will try to calculate the, it will insert the time when the data is received. Then it will calculate the message, and it will insert the time when the data has to be sent, including the antenna delay. These are the two important timestamps will be used in the receiver transmitted side to calculate the exact time of the flight. Once data has been transmitted, all the message has been set, then here the receiver, the device B, will be sent the message. So this message will be transmitted back to the device A. So once device A receives the message, now device A has a final message will be where it will be having the timestamps of the messages sent by the receiver. Once the data is being received, it will do some frame, is a received frame as enough length is not 24, it's defined as a 24 bytes. Then it will compare the received message is proper or not. Once it verifies the first couple of bytes is all good or not, then it will go and try to extract the timestamp from the received message. So now the transmitter has a transmitter timestamp, pole TX timestamp, receive RX timestamp. The difference between pole TX timestamp and receive RX timestamp will give the T round, and and it also have a timestamps of the receiver, that is receive TX timestamp and pole RX timestamp. The difference between these two will be give T replay. Now difference between T round and T replay multiplied by some clock offset will give the time of flight, and the time of flight is multiplied by the speed of light will give the total distance. Now this distance I'm doing some moving average to get a smooth waveform, and then finally I'm printing. So you will be getting, this is the final message what we are getting. So I'll open the serial terminal for the graphical representation, and I'll reset the tag. So this is the lower limit, this is the upper limit 200, and this is the actual value. So you can read it here, we are getting around 60 centimeters distance. Right. So this is a demonstration of the single side two-way communication, two-way ranging of the UWB. So this is anchor and this is a tag. And now we can see the anchor and tag are apart from each other of 60 centimeters, and the value 2, the orange color line, denotes the distance between the anchor and tag is 60 centimeters roughly, like with plus or minus 10 centimeters tolerance. As we are moving this tag closer to the anchor, you may notice that there is a drop in the reading. The reading is slowly dropping. And when I move a little bit away, the distance between anchor and tag is increasing. So this way the anchor and tag communicate with each other